coordinator for this QT-09 course and the engineering foundations in quantum computing. So sir is also along with me. Sir is the coordinator for this course. So at this time, I will invite sir to share a few words. Then as Dr. Deepti will be leaving, so she will share a few words as a resource person. She is having an industry institution meeting in the MNIT. We are having that industry institution interaction today, and we are all tied up. So, but then Saula sir also took some time. I thank you. And this time, first Saula sir, Dr. Deepti will share a few thoughts. Thank you.
Deepti?
I think she left. I think, sir. She had a departmental meeting at this time.
Okay.
I think she left. You can start. Yes.
So, good afternoon, all my colleagues here and students. Thank you, Dr. Pilli, for giving me credit for doing nothing. So, you have brought out that lacuna here that I am not doing anything. So, I have highlighted that. Thank you. So, I'm here just to share with you all the kind of effort we are putting in for bringing few good things to you as a joint effort for 7 academies. And I don't know how to remove this. So what I'm going to do now is just to indicate you about the efforts of 7 academies jointly, and the way we have just planned to make it convenient for you to lead your pedagogical and other research areas at your own institute. At least we should start with the BTech kind of electives that way. So I believe most of you would have the minors in BTech at all of your institutes, and AICT already has given that list which we can offer at our own institute. So no other permission is required. No permission is required further. It is just your local body who can just allow you to integrate that list of minors for any specific field into your curriculum that way. So I thank all my colleagues who are chief investigators at other institutes, IIT Guwahati, Gaurav, IIT Kanpur, Professor Fani, IIT Jabalpur, Professor Ojha, IIT Roorkee, Professor Manhas, NIT Patna, Professor M.C. Singh, and at NIT Warangal we have Professor Anuradha. So we have actually putting in efforts jointly, and also thanks to my co-CIs at MNIT, where we are actually doing even more efforts beyond those to bring you with kind of a consolidated certification if you have done 4 or 5 courses to one area. We'll come to that later. So the credit for quantum courses, let me just briefly highlight the point here. Dr. Emmanuel Pilli, professor in computer science, who is leading this course program, he is also leading the series of the quantum for 11 programs. And thanks to him that we have actually a good presence among all the institutes around our country. And all 7 academies also have joined to spread that word about quantum across our whole country. So we are proud that we are part of that part, the kind of efforts with the DST and AICT, thanks to DST and AICT also. I'm just highlighting you the way AICT or UGC has given us, all of the institutes, approved institutes, a mandate to float honors and minors, and no additional approval is required, right? So what AICT says, we can have about 18 credits in a specific field. If that field is what we say, if that field is
Emerging.
Yeah, I'm just trying to have my pointer, which I'm not able to get. I don't know, something is wrong. Okay, I'm not able to write anyway, no problem. So I will just do with my cursor some way. I think something is stuck up, not a problem. So the first line says about 18 credits in a specific field. If that field is actually in your BTech area, that is called honors. If that subject field for 18 additional credits is beyond your area of BTech, not your area, the offered BTech course at your place, and then this is called minor. So a computer science can float a minor in robotics, which is more close to mechanical or a cross-disciplinary, or a mechanical people, the BTech people can opt for minor in computer science or something like that. So we just saw that AICT recommendations. I'm just putting it in front of you so that you can also get a confidence about running those courses and teaching at your own place. That is the sole objective of this interaction, which we are now leading, led by the 5 academies, and specifically for quantum, led by Dr. Pilli. This is the 3 or 4 the kind of links are there for AICTE. I will share slides with you. Maybe in the chat you can download, or maybe in the canvas we'll put that slide so you can look at those links detailed way little later. Okay, so my slides are stuck up possibly. I'm sorry, my slides are stuck up. So these links you can actually see at later part. I don't know, something is stuck up. I'm sorry. I will prefer this where I can browse it actually, and I hope I can browse. Okay, something is wrong. If I'm sharing, I am not able to browse. What could be the reason? I don't know.
Maybe you can show like this, sir. This is.
No. Have you given me presentation rights? I don't know. Deepesh, can you give me presentation rights? Are they
Yes,
solely
sir.
with me?
You are presenter, sir.
Okay. I'm not sure. Something is wrong. I'm not able to browse. Maybe my keyboard or something.
Sir, you can show like this, sir. I think without making it full screen, I think you can.
Even then, I'm not able to browse actually.
Oh, okay.
My key is not working. My mouse is not working. Anyway, I just read my slides. If that browsing is allowed in my system, no. I think my PowerPoint is stuck up.
Sir, you can share with me. Maybe I can post from here.
I will do that.
Sir. Deepesh mail ID, sir. fdp.eict.
I'm sorry, I could have checked it earlier. Anyway. So what AICTE has proposed is for all different fields, they have given the list of minors, and they have given about 6 courses in quantum, where we have jotted down a few things that we can actually spread that around 10 to 11 courses, right, Pili? So you can choose any 5 of 11, and academies would be happy to certify you with a consolidated certification that you have done a complete course for equivalent to 6 months in that a specific field of that whatever you do, especially for this program, the quantum, that way. So I'm not sure. And the list, I think I will request Dr. Pilli to display with you. The slides are not working on my system. I'm sorry.
Yeah, we are sharing, sir.
And and then the point is the minors are offered in many fields, including AI, machine learning, data science, and computer vision, VLSI design, even power systems, smart power grids, and all those kind of things. So we have jotted down those. Soon we'll float the scheme for quantum, especially where we'll have possibly Dr. Pilli is planning for some 1 week interaction in person, and then we'll be able to go ahead with the consolidated certification. We are also waiting for AICT nodding for that, so that we can use their umbrella to give you that. Yeah, third or fourth slides, please. Thank you very much. Next, please. Yeah, next one. Yeah, so they say that they all, please, previous one. Previous one. Yeah, so AICT says, the letter came in 23. They say all emerging areas you can offer, they have given an indicative list only. And they have given the list of courses and indicative titles only. So you can offer your minors in your different branch on these topics, or you can offer the major in these areas if they belong to your BTech field that way. So both things are open. Please, next, please, Deepash. Next, please. And they say 18 to 20 credits can be done. They say it can be transferred from SWAM also. But now we are offering that we have a live interaction with the speaker. Your problems are immediately addressed, and we have live quizzes, and we have live interaction also. So there is an advantage over the MOOC platform. So we have just floated that part. Next, please. And this says that you can do only 10 credits from MOOC, and any qualified faculty can offer and teach these minor related courses. That's what ISAT has mandated. There is no permission required for anybody else. Right. Next, please. Yeah, next, please. This is about even more other fields from UGC that way. Yeah, next, please. So both our higher education bodies have propounded that. Now, salient features of our program is we are trying to have a collaboration with standardizing agencies, the skill councils. We already have interacted with the ACT UGC for support. DST is sponsoring these quantum programs. And we are also planning in future, if you could have the DigiLocker insertion of your certificates, and maybe in very far future, not very near future, we could implement the credit transfer so that the courses of AHT Academy may become replacement for MOOC or other kind of regular courses, even for your MTech or PhD. Next, please. So I will just not take much time. These are the courses. These are the areas, broad areas, among which we offer the courses, and almost all of them we cover as a minor also. So we offer at least 5 or 6 courses in a year, like that. So we don't offer it in a season. A season might have, yeah, this next table, please. So this is the list we have offered this season, January to June. And whichever courses are being left out from that subset of 5 courses will be offered in the next season, July to December, that way. Please go ahead. These lists are available for every academy. You can see that our site also. Yeah, next, please. So I will just stop here, indicating to you that this is a list taken from the AICTE. The first 2 columns, or first 3 columns are from AICTE. They have given this list where they have mandated all of us as a faculty. We can offer quantum as a honor into the computer electronics, or as a minor in all other branches that way. And we have aligned our courses. In the last column, we list that we have aligned our offering of the courses in quantum just similar and on the lines of the AICTE. So I'm sorry, I have just created some disturbance in the continuity and taken a little more time. Thank you, Dr. Pilli, and I hope all participants to be aware that these speakers are all exponent in their own fields. So let us get benefited from their exposure. And also thanks to all these speakers who have kindly agreed for sparing their valuable time. And I will also like to take opportunity to thank our director, Professor N.P. Padi Saab, for allowing us and encouraging us to offer these courses on different lines and performs few innovations in this pedagogical domain. Over to you, Dr. Pilli, and thanks to you also for putting a lot of efforts and including you with other other coordinators, other academies. So I am thankful to all of you for offering this course and making me part of it and partly. And thanks again for highlighting that I haven't done anything. Thank you very much.
Sir, yeah, thank you so much, sir. Your guidance is sufficient. We will do the remaining. So thank you so much for joining and sharing the vision that we are trying to do. We have faculty who joined, who are joint principal coordinators. Dr. Vartika Agarwal from IIT Guwahati and Dr. Deep Prakash Samajdar from IITM Jabalpur. I'll request them to share a few thoughts. Then we'll go over to Deepti ma'am from IIT Kanpur. You can share a few words of greetings. Yeah, over to you. Vartika ma'am or Mazdar sir, one of you can start. Yeah.
Let me start here. So thank you, sir, for giving me the opportunity to say something on this platform. So, first of all, I would like to congratulate you for conducting the 9th part of this wonderful series of lectures. And as per the feedback received from the participants, they have got to know a lot of things regarding quantum technologies or quantum computing things in this series of lectures. And I really appreciate your efforts in making this series a huge success. And I would like to also congratulate the participants from the faculty members from different colleges or institutes would be the part of this historical series, I would rather say, and learn a lot from the experts in this field of quantum computing. And as we all know that our government is putting a lot of efforts in educating us in this field. So it would be really beneficial for you all in becoming a part of this FDP. So good luck to all the participants. Thank you, sir.
Thank you. Thank you so much, sir. And it's been a joy. He's been there with many courses with me as a joint principal coordinator from IITM Jabalpur.
Right, sir.
Thank you so much.
Yeah,
and he'll be taking few sessions also in this course. Participants need to be appreciated because you have continued the journey. And many of you have, some of you have done all the courses, I would say. I am really amazed. I really want faculty members, and there are some students also who've done all the courses that have been offered, and it's a really a very I really appreciate many of you. If I was sharing with him also, Mr. Deepesh, who is maintaining the data for us. About 5,000 people have done their training in various programs individually. But if you look at 800 people have done 6 or more courses, 800 people have done. So that's a phenomenal this thing. And as a contribution, as Professor Saula was just mentioning, we have about 300 hours of recorded content freely available for anybody in the world. Of course, mostly for us, for our countrymen and women. So we have, that's a big contribution. I am so happy for that this platform, AICT, National Quantum Mission, DST, and the Ministry of Electronics and Information Technology, the EACT Academy, and all our esteemed institutions, they have given us a platform to create this content, and it is available for all of us to use. Thank you. Thank you so much, Dr. Deep Prakash. Vartika ma'am or Deepti ma'am, you would like to say something? Professor Manas has joined from EICT Academy, IIT Roorkee. Professor Manas. You're there. Yeah, I think that should be fine. So, Anil sir, maybe you can take 5 minutes before we ask Dr. Jaykumar to begin his. He can greet and begin his lecture as well. Anil Kumar sir, if you would like to add few words from AP State Council for Higher Education. Schedule. Yeah, so meanwhile, let us look at that. I think sir has already shared initially at the beginning. So this course is again a very specific, unique course that we are looking at as we look at. So this is the schedule that is tentatively planned. The topics are all fixed. There is one speaker I just want to confirm because there is some permission that is required from the industry that she is employed with. So once that comes through, we will announce. So as of now, we will start with Dr. Jaykumar Vaitishankar. He was supposed to take a later date, but because of some program schedule in our institute, we had requested a few. So suddenly he's there. Yesterday I requested him. Today he has agreed to be with us. So he'll be dealing with. This is a course which is in engineering foundations in quantum technology. So all the aspects will be shared, and an equivalent to the quantum computation will be discussed. So where these contents will be used is what is going to come up. And we'll have definitely one or two industry experts also coming in shortly. So we'll start with basic computer architecture today. Then we'll go on to communication, which will be the analog communication part, which Dr. Rajendra Mitrawal will be taking. He was the coordinator for QT-06, as most of you know. Then we'll have the electrical part, that is the RLC circuits, the resistance, inductance, and capacitance circuits, and of course some more transmission line basics. So this will be led by Professor Deepthi Saxena from MNIT Jaipur. Then we'll have a break on April 15th. That is because of the Vaishakhi festival, which maybe most of the North Indian states will also celebrate. So that's where we'll try to take a break on one day. And then from 16th onwards, hopefully we will have a full understanding on what usually we call it the theory of computer science, theory of computer science, or formal language and automata theory. And we'll discuss the various languages. So we'll have Ms. Nivedita De, who will be dealing, and she will be correlating these to the concepts of quantum computing. Then we'll move on to some industry lectures on quantum sensing and quantum communication, and linking these engineering aspects to that. Then we'll start with noise for two lectures. Dr. Deep Prakash Samajdar will be taking introduction to the noise. Then we'll go with the part that is left out, that is Turing decidable and Turing recognizable languages and the complexity theory by Dr. Mustafizur Rahman. Then we'll come back again on Saturday also, P and NP problems, NP hard and NP complete problem will be shared by Dr. Mustafizur Rahman. Right. Then coming back to the noise part, we'll have Dr. Ashwath Babu doing the lectures. Then we'll go on to the part of cryptography, which we'll have Ms. Janani from IBM Quantum taking up. Towards the end on May 1st and 2nd, which are again Saturday and Sunday, Friday and Saturday, we'll have digital communication part, and noiseless channel encoding or noisy channel encoding part will be handled by Dr. Mustafizur Rahman. So we have a mixture of very good industry and very good academician combinations coming in for these lectures, and most of them are basically engineers, and they are having very strong engineering background and also a very good understanding of quantum. Most of them teach quantum, and they are also able to handle this part. So that's where we'll try to look at. And welcome for those who are participating for the first time. I think that this PDF will be shared in the this thing. What do you say? It will be shared in the WhatsApp group. So it's already shared. So please look into your WhatsApp group. You can get the schedule. The sequence is fixed. Only the speakers, there may be slight change. We'll let you know in the days to come. But the first 5 lectures till Dr. Deepthi Saxena, till we have a break in Vaishakhi. Till that date, the speakers are confirmed. And I think that's the whole content for you before you, and we will try to take it forward, right? And maybe we'll have a brief kind of celebration on World Quantum Day, April 14th, which is coming in that. This came in the second course actually, and we had a big meeting last time with many experts coming in. But because of a lot of activities happening in the Amravati Quantum Valley on April 14th, many of the resource people will be there, like Dr. L. Venkat Subramaniam, C.V. Sridhar, and all. So we're trying to see how we can do. We'll try to do something definitely as a part of that activity, right? So I think without taking much time, I think we are on time, 3:30. Over to Dr. Vaitishankar, Jaikumar Vaitishankar, and he will begin this lecture. He is well known to you. So I would, anyway, still some people are joining now in this course, and congratulations, we have touched 500 participants, and that's also a very good sign. We have with us Dr. Jaikumar Vaitishankar. He's an IBM educator. That is his qualification. He's an expert in Qiskit, and he's been doing workshops across the country, and many of the IITs, IISc, Bangalore, and many places he has done. And he has done a special training with IBM and IIT Kanpur. And also, he's also a student, right? Even if I do some courses now, he's also a student. Wherever I register, he's also registering as a student also. So he's he's like a continuous learner and also a trainer. But he's qualified by IBM to teach on quantum computing and also on Qiskit. So he has extensively done a lot of lectures in the earlier days, especially QT-03, which is a laboratory course. He has done on Penny Lane, he has done on Qiskit, on CIRQ, and also on Quniverse. All these tools he is well versed. And also he has done a lot of computational background courses that were needed for this thing. So he's well known. But of course, if you would like to attend the previous lectures also, I would like to share those links shortly in the group. So QT-01 to 08, all the lectures are available on YouTube. Many of the lectures have been taken by Dr. Vaitishankar, and one table, QT-1 to 8. So just before sir starts, I'll just give you so we just take 1 minute, because we'll just give you a snapshot of what has happened from February 28, 2025 to April 2nd, 2026. We conducted about 12 courses covering about 9 courses, starting from QT-00 to QT-08, all courses. 3 and 4 were merged, 00 and 01 were merged. But in that sense, we have repeated sometimes some courses. So totally, we have done 12 courses in all, and number of registrations have definitely been more than 10,000, and number of participants also have come, and we have certified also many. And you will also be very happy to note down the kind of what do we say? The simple post is about to come. An year on quantum learning is what I would like to title this. So we'll just share that once, and then of course there are few people whom I should thank personally. Professor Dr. L. Venkat Subramaniam was the main brain behind this, who was the leader of the quantum group in IBM, and these are the programs that have happened. Share correct? Share nahi kare na? Share. So Dr. L. Venkat Subramaniam, Dr. Mani Madhukar was from IBM, and at that time the chairperson of AICTE, Professor T.G. Sitara, and the mission director for National Quantum Mission, Dr. J.B.V. Reddy. Of course, our director, Professor N.P. Padi, who has been the guiding force behind all these. And these people have helped us to put together this whole course, and you can see all these courses were conducted. So about 12,008 participants registered. 10,747 people have received certificates in these 13 courses, which were completed in a period of 13 months, maybe starting from March 1st to April 2nd. You can see, think like something like that. 13 months, 13 courses we have done. 10,747 people certified. Faculty are 8,630. So in this 8,630, there are repeated people, of course. These are certificates, individual certificates, but people may be common. There are about 400 PhD holders. So that is something which is unique, and I'm very happy to share that. Industry participants were about 216. PhD students were about 888. UG, PG were 752, and other project staff and others were 261. So totally 10,000 plus people have been certified. That's a great achievement that I would like to share. And the people whom I am named are the people who are instrumental. एक बार वो नाम दिखा देना ऊपर चले जाए paragraph second paragraph. So these are the people: Professor T.G. Sitaram, Professor Abhay Karandikar, Dr. J.B.V. Reddy, Professor N.P. Padi, our MNIT director, Professor Vineet Sahula, and then Dr. L. Venkat Subramaniam, Dr. Mani Madhukar, and myself. So we have been doing, and there are a list of speakers also named Nichan or Nichan. And then, of course, we have Professor K. Madhumurthy, Professor Anil Prabhakar, and of course, Dr. J.B.V. Reddy and others, and Dr. Anil Kumar from AP State Council for Higher Education. They have formulated the second sequence. So we have done that. And these are the speakers whom we have seen: Professor Anil Prabhakar, Dr. L. Venkat Subramaniam, Mr. C.V. Sridhar, who is now heading the Amaravati Quantum Valley Initiative, Dr. Bhaskar Kanseri, Dr. Anindita Banerjee from CDAC, Dr. Bhaskar Kanseri from IT Delhi, Anupama Ray, ma'am, she's from IBM, Mustafizur Rahman from IBM, Ritajit Majumdar, Richa Goel, all from IBM. Ms. Nivedita De will also be a speaker, Dr. Santosh Parthi, Dr. Ashwath, Dr. Jaykumar Vaitishankar, Ms. Janani, Arka Mazumdar from CDOT, Anand Raman from Anutantra, Arnab Kumar Ray, Yash Vaswada, Harish Sahu from DRDO, RP Singh, Professor RP Singh from Physical Research Laboratory, Professor Kallol Bhattacharya from he's from University of Kolkata, and a list of speakers from Jaskaran Singh and Dr. Chandra Rao Yella from Hyderabad Central University. So all great people in this thing, and we have brought them together. So this will shortly come as a LinkedIn post. You can read slowly, and the remaining two lectures also coming up: QT-10, solid state physics, and QT-11, which will be quantum optics. They will also be held in month of May and June. Thank you so much, all participants, and over to you, Dr. Jaykumar Vaitishankar.
Thank you so much, sir. Am I audible?
Yeah, sure. Yeah, Devanshuji will put it as a LinkedIn post. So I think today or tomorrow you will be able to see. Thank you. Over to you, sir.
Thank you, sir. Thank you so much. Good afternoon to each and every one of you. I welcome you all for this wonderful FDP series. I'm more excited than the participants each and every time. If they are giving different topics, then I need to work on more. Anyway, it's my pleasure to do that. Thank you all. So today, let me share my slides. Okay. Is my screen visible, sir? PowerPoint.
Yes, sir. Yes, sir.
Okay, thank you. So once again, I welcome you all for QT-09 Engineering Foundations of Quantum Technology. So under this series, the first topic is we're going to cover about quantum computer architecture. Okay. So most of us know what is a computer, and most of us are using computer on day-to-day life basis. Definitely, I will share all this material in Canvas portal also. Don't worry about material, just focus today's session. So what is a computer? In earlier days, we used a vacuum tube. Then slowly we evolved to this much of big computer architecture. The computer is very huge in those days. Okay, it is like a very big machine, can cover up the entire room. Okay, so computer is a device, computational device, a device which could do a computation. We can call it as a computer. So basically, we need to give some input. So we need to do some process to obtain the expected outcome. So this is the basic definition of computer. It could be any form of computer. It could be mechanical, it could be analog, it could be digital. So if you are looking at a mobile phone is also basically a computer. It doesn't have a keyboard. It contains interface, touch interface. So if you are clicking the typing tab, the virtual keyboard will come. It is also used like an input. So virtually you can convert any device which can be able to get the input, will do some process, will produce some desired output. It could be a computer. So if you're looking at the mainframe architecture or supercomputer or data center, okay, this contains multiple computers. This contain multiple computers, right? So if you're looking at warehouse level computing, so supercomputers, large scale computers, okay, Google, Amazon, IBM has humongous amount of computer clustered together, which is called warehouse scale computer. Maybe you can call supercomputer facility or high performance computer facility. So all these computing facility need to have cooling towers. They need to have power substations. So whatever the chat GPT, definitely you can see PPTs, you can rejoin. If the PPT is not visible to you, you can rejoin. Okay. So basically all these supercomputer high performance computing facility need to have two important components. One is cooling factors, cooling towers, one is power substation. So whatever we are doing right now, we are using ChatGPT, we are using Perplexity, we are using Google Gemini. All these AI model requires humongous amount of power. So if you want to scale it up, it will not be sufficient or sustainable in future. So that is the problem we're going to face in future. So that is why we are looking for alternative computing, just like quantum computer. Okay. So we have a series of discussion about what is a quantum computer. Imagine if devices are speaking among themselves, discussing among themselves. So it is just like a cartoon. I want to convey this information through a cartoon kind of information. Okay, a laptop is asking, so what is a quantum computer? And a CPU is telling it is a computer built by using quantum physics. So normally the classical computer, what we are using is based upon digital electronics. But a quantum computer is entirely built upon quantum physics, not a normal classical physics, what we are using right today. Right? So the device is asking whether all computers are built on same physics, but why quantum is any different. So it is a very long story. We need to cover up through a historical perspective. Okay. So you can imagine whether the device is faster than all the devices produced earlier. Definitely, the quantum computer can think and process millions of tasks within a fraction of seconds. Definitely, it is fundamentally different. It is cleverer and superior than whatever the devices we created so far. So it lives in the coldest climes and it is both fragile and sharp, which is contradictory and oxymoron. Okay. If you want to define quantum computer, if you want to understand quantum computer, initially it will confuse you because it involves with quantum physics and quantum mechanics. And what is the capacity of a quantum computer? It could be able to solve the hardest problem of the world. Okay, so generally, if you are deploying for a quantum computer, if you're going for quantum computer, you need to go for only solving hardest problem, which is not possible by classical computer or a supercomputer. Then only you need to go for quantum computer. So whether we can use the quantum computer to or it will make to create a graph, it will do, but definitely we cannot do any of this application. So quantum computer never going to play music for you, never going to do shopping website, never going to make a graph like a Excel or PowerPoint or Word. Okay, definitely these problems are not focus about quantum computing. So you can ask finally this question whether quantum computer exists. Yes, it is very difficult question. It will not exist in full-fledged real-time application solving machine. Okay, all the quantum computer existing in this world right now, it is in R&D level, it is in baby state. You can compare today's quantum computer facility with 1940 classical computer. Okay, so we evolved so much from 1940. We are in very advanced level in classical computer. Same thing will happen for quantum. We need to wait for minimum 15 to 20 years to solve real-time problems. So this is the catch. This is the conversation we went through between devices. So why we need quantum computer? So all these courses, all these topics, definitely it need to touch with quantum computer. It need to relate with quantum computer. So with the known knowledge, we are able to observe the quantum computing knowledges through these slides. Okay. So it is inevitable question. Why we need actually a quantum computer? We need to ask few questions for this. The first question is, how long Moore's law will hold, and how we can solve all problems within given enough computing power. Okay, so even though if you are keep on scaling the supercomputer, if you are building a generative AI model, ChatGPT, Google Gemini, it will not help to solve all our problems. Most of our complex problems are never able to solve through supercomputer. So this is the genuine open-ended answer, right? So quantum computer are not intended to replace the classical computer or supercomputer. It will exist like brothers and sisters. So in future, if you want to use quantum computer, always you need to have help with classical computer. So side by side, you need to use both classical and quantum computer. So quantum computer never going to replace classical computer. Always remember this, always insist among your students. So most of the participants will think whether quantum computer going to replace classical. Never going to happen. So what is the motivation? So from 1940, microprocessors have revolutionized our world. So whatever the device we have, like cell phones, like technology, internet, rapid advance in medicine, everything came through a microprocessor revolution. Okay, the semiconductor industry has grown from $21 billion from 1985 to $755 billion in 2025. So Indian government investing 2 lakh crore in semiconductor industry. So until 2020, all these 2 lakh crore invested in semiconductor industry. Okay, so once we have solid semiconductor industry, then we can develop quantum industry. Okay, so initially all this fund is allocated for industry, but after 2030, Indian government having the plan to invest 2 lakh crore in quantum computing. So without semiconductor, we cannot achieve quantum supremacy or quantum machines. Okay, you can see all these applications, devices, everything evolved from microprocessor revolution. So this microprocessor revolution, okay, started from Silicon Valley. Okay, Robert Noyce is called mayor of Silicon Valley. So he is the main pillar to co-found a Fairchild semiconductor industry in 1957. So if you look at developed countries, all those developed countries have very strong foundation in pure science. Out of pure science research, engineering domain evolved, keep on evolved, right? So he co-founded Intel. So most of you know Intel company. So each and every computer we are using right now have Intel processor. Okay. So he co-invented integrated circuit. So this is most promising, ever revolutionizing theory in computer science or electronics. Due to integrated circuits, we are able to reduce the circuit size from vacuum tubes into a small level chips. So based upon this, based upon the maybe yes. So we need to answer this question, whether Moore's law going to end. So anybody from EC or CSIT, most of you know Moore's law. Okay, so Moore's law is a law founded by formulated by Jordan Moore. It is a prediction. So what he predicted, we can expect the speed of computer to double each and every 2 years or so. Maybe I will zoom for you if it is not visible. Okay, so he is a person who is the one of the co-founder of Intel in 1965. He predicted a law, or he predicted a strategy. Each and every 2 years, the computation power will get double. The speed of computer will get double. Okay. To understand this, we need to understand the core part of computer, the core part of CPU. Okay. The processor is core part. So processor contains billions of transistors. So processor contains billions of transistors. Okay. So these transistors are fundamental computation units. Okay. So what is the law predicted over here? Each and every 2 years, the computation will get double. So how will you increase the computation power? How will you double the computation power? By doubling number of transistors. Suppose in 2024, you have 1000 transistors. In 2026, you need to double 2000 transistors. You need to double the number of transistors. Okay. If you want to double the number of transistors, you can do easily. But the engineering challenge is you need to reduce the size and you need to keep the same processor area. The processor size remains same, but you need to reduce size of transistor. So this is the engineering challenge we have, right? We cannot scale it up just like that. We need to reduce exactly half of the size. So each and every 2 years, you need to reduce half of the size. Okay, theoretically it will be easy, but practically it is almost impossible after some point of time. Okay, so if you do, what happens? The processor size become cheaper. Okay, the processor size will keep on remaining smaller in form factor, right? But we need to understand what a transistor will do. A transistor is simplest form of processor. It will act like a switch. It will act like a switch. Normally, the transistor size will go for 10 nanometer in size. Okay, if you allow your transistor to pass electron flow, okay, it will represent on state. If your transistor is not allowing your electron flow, it will represent off state. So you can represent 1 and you can represent 0. You can represent 2-level system, binary logic, using this small device. So this is fundamental unit. And what is the engineering challenges? Each and every 2 years, we need to reduce the transistor size. Imagine in 2026, we have 10 nanometer. In 2028, you need to reduce up to 5 nanometer. Okay. So what happens if you reduce transistor size less than 4 nanometer? Can anybody want to answer in chat box? You can answer. If you reduce transistor size less than 4 nanometer or 2 nanometer, what happens? Please use chat box if you know. Yes, sir. Quantum effects will come into start. On what type of effects? That is the question. Exactly. Great. Most of yes, sir. Most of you attended previous session, so definitely able to answer. So quantum effects will come into play. So there is a fundamental size limit applies in nature. Beyond that limit, you cannot reduce transistor size. Okay, quantum effects will come into play. I'll zoom in. And this is very important part. Okay. Quantum tunneling. Somebody answered exactly. Quantum tunneling. So quantum tunneling will make electrons to jump and flow even the switch is off. Okay, so if you are using fan, imagine if you are using fan, the switch is connected to fan. Okay, if you switch on, you are giving power supply, the fan will get operated. If you switch off, you are stopping the power supply, the fan will get stopped. What happens if the switch is on, even though the fan will get stopped? If the switch is off, even though the switch is off, the fan will get operated. So it will go beyond your control. So the same thing will happen in the case of quantum tunneling. Okay, so this 0 become 1, 1 becomes 0 automatically without your control. It means your device will go out of your control. If your device go out of your control, you cannot use that device to represent your data, to compute your data. So fundamentally, somebody told the exact answer. If you reduce transistor size 1.8 nanometer, okay, quantum effects will come into play, quantum tunneling will happen. It means 0 become 1, 1 becomes 0 automatically. Okay, your system become unstable. You cannot use that device to store and process your data. Okay, you cannot believe your device. You cannot use it. No more. Exactly, sir. So he is most important person in semiconductor industry, Jordan Moore, co-founded in Intel 1968 with the Robert Noyce. Okay, so this is the law we covered in previous slide. So each and every 2 years, the computational power will get double. The speed of computer process will get double. Okay, so since 1975 until 2022, we able to achieve this increase. We able to achieve this Moore's law. But after 2022, we cannot reduce transistor size. So this is very big problem we are facing right now for EC department, for EEE department. If you are not able to reduce transistor size, okay, you cannot create powerful processor. If there is no powerful processor, IT and CS industry cannot upgrade their hardware. If they are not able to upgrade their hardware or server, they are not able to take challenging projects. So this will lead to domino effect. It will lead to global recession. Okay, so if you compare what we able to achieve through Moore's law, if the same pattern followed in automobile, in today's scenario, you are able to get Rolls-Royce just for $100. Okay, so that type of development we achieve through semiconductor industry because of this Moore's law, because we are able to reduce transistor size. Okay, so let us formally begin our definition of computer architecture. So it is the programmer's perspective or functional behavior of a computer. So computer architecture is programmer's perspective or functional behavior of a computer. So generally 32 bits to represent an integer value. So if you are offering 64-bit computer architecture, then you can go for 64-bit. Okay, so according to your architecture, you can represent the exact amount of information. The more amount of bit you are able to process within a fraction of time, the more computation you can do. Okay, there is a slight difference between architecture and organization. Computer organization is internal structural relationship, not visible to a programmer. It is like a hardware. Okay, so you can differentiate architecture and organization. Architecture mostly related to software aspects or logical aspects. Okay, organization mostly related to hardware aspects. So it is based related to device design, right? Take an example of physical memory. Take an example of processor. So all these things will come under computer organization. Okay, so generally we have 3 parts in computation in computer. So it will have input output devices. Through input device we are feeding our input, and we have control unit, we have data path which comprise with processor. Okay, so this is the core part of your computer. Then if you go for memory, if you have large amount of data, you need to store for some temporary purpose or for permanent purpose. So we need memory also. Okay, this is the basic outlet. So we need to discuss about hierarchy of computer architecture. So if you are related to CS and IT, please bear with me. So we have different types of faculty from physics, chemistry, maths. So we need to talk from basics, from scratch. Okay, so we have two aspects. One is software, one is hardware. So we have a boundary. We have software hardware boundary, and those are integrated by instruction set architecture, which is basically called ISA. Okay, so beneath hardware, we have instruction set, and we have input output system. So all your keyboard will come under input output system, keyboard, mouse, joystick. Okay, all these input output devices, printer, right? Your monitor. Okay, so all these stuff are managed by micro program. So we have a little bit micro program. All those things we can able to manage with micro program. So beneath that we have data path and control, like buses, wires. Okay, so bridges. So all this will come under data path and control, which are manipulated by register transfer notation, which is called RTN in short form. So beneath that we have digital design. So we need to design all this hardware in case of logical diagrams. Okay, so beneath that we have circuit designs. So initially we have digital design. According to that logical design, we need to build circuits. Okay, deep devices. So finally we have layout in the form of chips. Okay, if you look upside, we have machine language programming. Okay, then we have firmware, we have BIOS, all this stuff, okay, which is related to software management, like compiler. Okay, so beyond this, we have operating system. Okay, operating system will control all your computer. It is a software part. It is a software part, which is very important. So nowadays you are using Windows, right? Windows is an example for operating system. So alternatively, Linux is there, Ubuntu is there, Red Hat is there. Okay, Kali Linux are there. So multiple types of operating systems are there. If you are using Apple, we have Mac OS. Okay. So this firmware controlled by assembly language program. So we need to discuss all this stuff in upcoming slides. Okay, so based upon all this stuff, we created application. Take an example of MS Word, okay, Excel, PowerPoint, all these application, example WebEx, all these are application. Okay, to run your application, definitely you need to have hardware. To interact with your hardware, you need to have OS, operating system. Okay, so all these parts will act like translator between the user and the machine. So whatever you are talking, whatever you are writing, everything in the form of high-level language. So all this high-level language will broken down to assembly level language, then broken down into machine level language, then broken down into binary language. So this is the flow. So if you have any doubt within this slide, you can put in chat box. No doubts means we can proceed. Is it clear? Okay, great. Thank you. So the whole upper part is software related. The whole downside part related to hardware. And to understand the computer and hardware, okay, we need to understand analog and digital signals. Okay, so there are two types of signals, analog signal and digital signal. So whatever the signal you're going to observe in this entire universe is analog in nature. Okay, so we need to convert this analog signal and we need to manipulate according to our device. So analog signals are natural one, digital signals are humanized one. Okay, we humans, we convert that analog signal and we try to mimic in digital form. So analog signals are continuous, analog signals having infinite ranges of values, Analog signals are more exact values, but more difficult to work with it. So that is why we left analog computer, we forward to digital computer. So initial days we used analog computer. Okay. In case of digital signals, most of the signals are discrete. It means it is non-continuous. Okay, you can divide your signal, you can easily control, you can easily manipulate. Okay, mostly we try to cover all these discrete signal in finite range of values. Only 2 values. It is limited because we need to represent in 2-level form, binary form. Okay, it is not exactly as analog, but easier to work with digital signal. That is why we are more prone to digital signals. Take an example of a digital thermostat in your room or in your AC, which displays temperature of 72 degree. But the same temperature, if you are measuring an analog thermometer, it will measure room temperature to 72.482 degree. So analog value is more continuous and more accurate, but digital value is more than adequate for the application and significantly easier to process electronically. Suppose if you are controlling your AC, you need not to know 22.375 degrees Celsius. Just 23 is more than sufficient for you to know and control. So this is a classical example. So analog signal can vary according to the time. So each and every time slice, okay, analog signal will keep on varying. It will contain maximum and minimum values. It will either go through positive value or it will go for negative value also. Okay, it could be a periodic and it could be a non-periodic. So all these concept we need to revise if you forget, if you're not handling all these courses. So generally, we need to have 2 common analog signals. One is in sine wave form, one is square wave form. Definitely, I'll share PPT, so don't worry about this material. Okay, so this square wave is not digital signal because it contains minimum value in negative. So that is why most of the signal which resemble to digital form will not be a pure digital. Okay, have you? So all these signals are analog form. Okay, sine wave is continuous, square wave is also continuous. Okay, but you can see the various variety of platform like random periodic, like our heartbeat. Okay, our brain wave. So it could be a random periodic. So part of the analog signal we need to understand. See, so each signal will have the amplitude. So amplitude from the horizontal line will have the peak, and also we have downside in negative phase. So I can measure amplitude in 2 different forms. Okay, from the horizontal reference line or the whole signal range. So period you can take from the starting point until to the ending point, the entire cycle. So if you want to calculate the frequency, it is invert to its period. Okay. So more the frequency, you have less the period. Okay. So if you are not able to see PPT, please rejoin, sir. Please rejoin. So we need to understand our signal and we need to represent this signal to logic. Okay. So before examining to a digital signal, we need to define the logical levels. So what are the logical level? We need to represent logical state in discrete form, in 2-level form, which will define a digital state. Okay. So generally all signals are in analog in nature. So if you look at microscopic level, even in your CPU, most of the signal are in the form of analog. Okay. So we need to have 2 logic. What is the 2 logic? Logic high. So whatever the logic typically have 5 volts. Okay. We can represent like high voltage or high level signal, and logic low you can represent typically 0 voltage. But if you are looking at your signal, it is continuous form. Okay, from 0.0 until 0.8 you need to consider like logical low. Okay, then from 0.8 to 2 voltage you cannot use this range. You need to use it like a threshold. From 2 to 5, you can consider like high level logic. So we are using binary system. Okay, what is the what it contains? 0, 1. So 0.8 to 0, 0.0 to 0.8, you can consider like 0. Okay, 2 voltage to 5 voltage, you can consider like on. So what you can understand basically, all signals are continuous analog in nature. We try to convert into digital. Okay, digital is human made. So digital signal commonly we need to represent in the form of square wave or clock pulses, clock signals, right? So this is what we covered in previous slide. It should be periodic. Okay, if it is periodic, it will be easy for us, or it could be a non-periodic. So whatever we compare this slide with previous slide, you can see there is no negative state or negative phase. Only in positive cycle we represent all our signals, right? So I can use pointer. So you can represent this signal as 0 and this part like 1. Again 0, again 1. Again this part like 0, this part like 1, 0, 1. So likewise, you can represent all your information. So like analog signal, you can have a characteristics of given signal pattern. You can find out the period. You can find out which is the rising edge. So this is the rising edge. So it is rising, right? So it is rising abruptly. So this is the basic difference. In continuous signal, it will vary continuously and smoothly. But here you can see abrupt rise. Also, you can see abrupt falling edge. Your signal definitely come from the top position to the horizontal level abruptly. So this is the basic difference between analog and digital. So I'll skip all this information. You can study on your own. We have limited amount of time. Okay. So what we need to cover at architectural level, we need to focus on programs, we need to focus on applications, all this stuff we need to achieve through transistors. So whatever you are thinking at program level, software level, you need to think at device level also. So that is the prime objective of computer architecture. Okay, so we need to understand electrical signals. So what are the various form of electrical signal? It could be discrete, it could be at atomic level, atomic elements, elemental level. It could represent binary values. Okay, so we can consider all these devices in the form of a switch. So we covered in first slide, right? Transistor will act like a switch. So mostly, fundamentally, all the digital devices will act like a switch. If you are giving input, okay, your device will decide whether to carry forward your input or not. Okay, if it is carry forwarding, it is operating on your input. If it is not carry forwarding, it is not reacting to your input. Okay, so basically the computation will done by with the simple logic of a switch. So all your computer, it comprises millions of billions of switches. You can imagine in such a way. So this is the representation of analog signal. Okay, this is the representation of digital signal, what we covered in previous slide. So we are revising. So based upon this, we need to create a digital circuit. So digital circuit contains multiple inputs and it will produce multiple outputs. Okay, so most basic idea about digital computer, you can relate it to form a digital system. Okay, so here you need to give digital input, you need to obtain digital output. So for that, you need to have conversion. You need to have conversion from analog to digital then you need to process digital signal, then you need to produce digital output. Finally, you need to convert into analog form. So 2 important things you need to do. So all your inputs are fundamentally analog in nature. Okay, you need to convert into digital input form, digital form. So this is called analog to digital. Okay, then you need to do all your computation, all your processing. So finally what you will obtain? You will obtain output in the form of digital. Okay, then again what you are supposed to do, you need to convert all your digital output into analog output. Okay, so here you need to do digital to analog. So this is very important point in whole computer. So what is the advantage of digital system instead of analog computer or analog devices? You can easily able to reproduce all your results. Okay, you can have accuracy of your results. It is more reliable than analog because analog system are prone to noise. That is why we left analog computer, then we turn into digital form. Okay, it is easy to design because if you want to design analog system, okay, you need to have special math skill. But for digital, you have minimum skills. Okay, and it is more flexible and functional. That is why we turn into digital system. And be able to program. But if you go for analog system, you need to use wires. You need to give all your input output mapping, which is much more complex. Okay, and you will get very speed computation most of the cases. So within 10 to the power minus 8 seconds, in nanoseconds, you are able to produce output. And it is also very economically feasible because of digital system, because of low cost integrated circuit. We are able to reduce cost from $1 million into $100 products. Okay, to understand a digital system, we need to understand number system. So number system could be classified into 4 categories. One is decimal, based upon 10 decimal values, 10 values, starting from 0 to 9, which is basically 10. And most of the digital system, you need to use binary logic based upon the 2 values, 0 or 1, true or false, yes or no. Okay, all these 2 values, you can go for binary system. And most of the stuff you need to use for octal. Suppose if your device contains only 8 level series, okay, 8 level computational basis, then you can go for octal. Then if your device contains 16 level of system, okay, then you can go for base level 16. So we will discuss why octal and hexadecimal we are using in computer science. So imagine why we are using decimal, because we have 10 fingers. So all these 10 fingers used for computation purpose. So we are starting from here. We are starting from here. This is 1, 2, 3, 4, 5. Then 6, 7, 8, 9, and 10. So with the help of fingers, our fingers, we are able to compute 10 quantities. Suppose if you counted 10, okay, if you want to count 11th quantity, you need to reuse the same fingers. So this same finger will be able to count for 11, okay. Then progressively it will go for 12, 13, 14. But after counting 10, whatever you are counting 11, you need to count with the help of your mind. So it is abstract computing. Okay, your computational device capacity will go beyond. Okay, so this is why you need to use memory. This is why you need to use your memory, right? So this is very good analogy. Why we are using decimal system? Because our base is 10. Our base is 10. So generally we are using decimal system for our day-to-day life. For computer, for electronics, we are using binary. Okay, so within digital system, sometimes we will represent in octal form, sometimes we will represent in decimal, hexadecimal form. So you can notice over here, so all these system, okay, have common thing for 0, 1. Okay, if you want to represent 2 in binary, your computation go beyond your capacity. So what you're supposed to do, you need to use these two symbols. You need to use these two symbols. So here I can write. So you have 0, you have 1. If you want to represent 2, you need to add 1 plus 1. 1 plus 1. So this is the binary logic, addition logic. Okay. So if you have 0, if you have another 0, if you're adding 0 plus 0, you get 0. If you have 0 as the input, and if you have 1 as the input, and you will get 1 as the output. So if you have 1 as the input, 0 as the another input, you will get 1 as the output. So until these three, you are able to understand. Okay. But if you're adding 1 plus 1, if you're adding 1 plus 1, what happens? It will go beyond your representation because you are running out of your symbol. So 1 0 will come to represent binary value 2. 1 0 will come if you want to represent binary value, decimal value of 2. So symbolically, you can represent 2 in the form of 1 0. 1 0. Okay. If you want to represent 3, then what you're supposed to do, we need to add 1 plus 2. Okay. Then you will get, look at the logic, 0 plus 0, what you will get? 0. 0 plus 1, what you are getting? 1. So according to this second law, according to this second equation, so 0 plus 1 will get 1, and this one will come over here. So this is the representation of binary value, binary value of 3. So if you want to represent 3, you need to represent with 1 1. So if you have any doubt, you can ask me, non-computer science people. Mechanical, okay, good, very good. So if you understand this logic, you can compare octal with decimal. Okay, so octal contains only 8 symbols, Okay, so if you want to represent 8, you cannot represent with the help of these characters, these symbols. Okay, so you need to reuse this symbol. So what is the best reuse? So after 7, you can create 1 0. So 1 0 will represent decimal value 8. To represent 9, then you need to represent 1 1. So all these 8 and 9 are not available in octal. So if you understand this, you can be able to understand octal. Already you know what is the representation of decimal, no need to discuss. So after 9, if you want to represent 10, directly you can reuse these two symbols. Okay, just like octal. But if you look at hexadecimal, beauty is there. If you look at hexadecimal, beauty is there because it can represent 16 symbols. It can represent 16 symbols. So after 9, okay, you no need to use 1 0 because we have 6 more additional symbols. A, B, C, D, E, F. A means it is equivalent to binary value 10. B means 11. C means 12. D means 13. E means 14. Okay, F means 15. If you want to represent binary value 16, then you are running out of your symbol. You need to reuse this symbol 0, 1. So if you want to represent binary value 16, in hexadecimal, you can represent with the help of 10. So if it is confusing, okay, so don't worry. Approach EC faculty, they will help you, or computer science or IT faculty, they will help you. So this table will give a very good example for you. 0 means decimal 0 means binary 0 0 0, octal 0 0 0, hexadecimal 0. 1 means only the last digit you need to represent with 1. Octal also last 1. Hexadecimal also last 1. Okay. 2, binary, you need 2 digits. Okay, whenever there is a whenever there is something happen between 2 power n, you need additional digit. So this is happening for 2, you need have additional digit in binary. Okay, so nothing problem for octal and hexadecimal. Look for 4. Okay, again 2 to the power 2, 4. You need additional digit, 3 digits here required in binary. Okay, for 7, okay, no problem until 7, no problem in binary. Again 8, you can see 2 power 3, you need additional digit, 4 digits are required. So this is the relationship between decimal and binary. Whenever there is a change in 2 power n, if you want to represent, one more additional device needed for binary system. Okay, look for octal. So what is the problem with octal? Whenever there is a problem power with 2 power 8 or 8 power n, 8 power n, we need additional digit. So until 0 to 8, we have single digit. But if you want to represent value 8, you need 2 digits. Okay. Now compare with hexadecimal. Now compare with hexadecimal. For 10, still you require single digits. Still you require single digit. So until 16, you require only single digit. Okay. So if you want to represent 16, then only you need to have additional digit like 1, 0. So this will happen at 16 power n. 16 power n. So this is very powerful demonstration. If you are choosing your value system, the entire device architecture will change. Okay. So basically, we will discuss most of the devices relied over physics about electron flow or electrons property. So most of the devices are made up of transistor and diodes. So above these transistor and diodes, we are using amplifiers and filters. So this will convert into a digital form. Okay, what digital circuit contains? It contains AND gates and NOT gates. Okay, with the help of all these gates, you can build logic over there. So what are the logic? You can add numbers. Okay, you can put in memory. Okay, if you do all this logical operation, then you can create microarchitecture. So you can transmit information between one device to another device. Okay, if you full-fledged develop the entire computer architecture, then it will involve with instruction on registers. Okay, so until this, you need to do with hardware. Until this, you need to do with all your hardware. But above this, you need to do with your software. All your operating system, your application software, everything you need to do with your software control. So I'll skip this. This is very generic and basic. So these are the components of a general digital computer. So computer contains CPU, central processing unit. Central processing unit, it contains both control and data path. In between your CPU and your devices, we need to have memory, because all your devices are very, very limited in terms of computation. So we need to keep something in memory, like our brain, right? So after 10 fingers, we are not able to physically look. We need to do mentally, right? So same thing. If your device go out of the boundary, then we need to use memory to store data temporarily as well as permanently. Okay, so I can interact with your computer with the help of devices, both input devices and output devices. Okay, so if you look at software level, you need to write application software which is written in high level languages. So if you come down, you need to write system level software. All your compiler and operating system are in system level software level. Okay. Then in hardware, you need to access your processor, your memory, your input output control devices. So you can look at this. So hardware, So hardware is comprised about the software system. Your software system is comprised about application software. So you need to interact all your application through system software. Your system software will interact with hardware. So your system software will act like a middleman, right? So what are the different level of program code? Generally, if you heard about C programming or Python programming, which is high level language. So humans are able to write, developers are able to write through high level program. Okay. So we have compiler. This is a software. This is a system software which will convert into assembly level program, which is intermediate level. Okay, so all these intermediate level program again converted into binary level. So this is machine level. This is machine level. Okay, so this is how we are working. This is our working. So high level language is the highest level of abstraction closer to our problem domain. So most probably we can do huge amount of productivity and portability if you are writing in high level languages, right? For faster execution, you need to convert to assembly level. Okay. For real execution, you need to represent in binary form, binary digits or bits. So this is what discussed in previous slide. Now we are able to understand how your computer works or how digital system works. Now we can distinguish between the software and hardware level by level. Okay. Normally, if you have supercomputer, you can call it as warehouse scale computer or data center, which will achieve high level parallelism. Okay. All your ChatGPT, Google Gemini, or famous tool called Cloud. Okay. Which is operated on supercomputers. Okay. Cluster computers. Okay, so this will do parallel request. Okay, multiple search, Google search, it will do parallel thread. So have multiple cores. Okay, so you can execute billions of instructions at the same amount of time, right? So you can execute huge amount of big data, if you are doing a parallel processing. Okay, so you can compare all this hardware exactly to a smartphone also. The hardware architecture almost resembles same. Okay, so what a small computer have it from a large scale warehouse, it contains a motherboard. So motherboard contains your processor means your core. Okay, your core contains next to it memory, and your memory interacted with input output devices. So this is a small layout of a computer, and computer contains multiple cores, multiple processors. Okay, so if you are taking a small core and if you are diagnosing into a small core, it contains instruction units. Okay, all these instruction units contains functional cores, functional units. So all these functional units converted into logic gates. So this is how you can be able to visualize and abstract your physical devices. So whatever we are using, laptop or computer or cell phone, it contains billions of devices, logical gates, billions of logical gates. So why computers become so complicated? Because we have great 8 ideas. Okay, so we need to design for Moore's law. So each and every 2 years, we need to reduce transistor size, half of the size, and we need to do abstraction to simplify design. And we need to make a common case at very fast rate, and we need to execute all these instruction in parallel form. Okay, so how will you achieve parallel form if you have multiple core? Okay, if you have multiple threads, you need to do pipelining. Okay, and you need to have multiple hierarchy of memories. Even if you're looking memories, there are different types of memory. So I want to highlight memories also. So give me 1 second. So you have processor, So next to processor, you have register memory. So next to register, you have cache memory. So next to cache, you have L1 cache and L2 cache. So next to cache, you have RAM. Random access memory. Next to random access memory, you have direct access memory. Devices can directly access your memory. Okay. Next to that, you have hard disk, or you can have SSD, or you can have NV SSD. So this is the hierarchy. Multiple types of memories are there. So we need to understand all this stuff. So what you need to understand, you need to design an algorithm so that it will determine number of operations to be executed over your device. Okay. So all your programming languages, your compiler, your architecture, all these will decide number of machine instructions for each and every operation. So each and every operation contains number of machine instructions. So recall previous slides. Okay. So all these logical gates executed by device instructions. Yes, you can put in chat box if you have doubt. Somebody raised their hand. No doubt? Okay, good. Then you need to consider about your processor and memory system. It will determine how fast your instructions are executed. So this is where you need to check whether you're going to buy a laptop. What is the processor generation? i5, i7 or i9. Okay. So based upon the processor generation, you can get the faster performance. And you need to identify how fast your input and output operations are executed. Okay. Based upon your keyboard, based upon your mouse, based upon your monitor, everything decides about the faster performance. Sometimes if your keyboard got struck, okay, there will be a delay by giving input for your system. Okay. Sometimes your system will hang up. During that time, you cannot give input. So due to delay in your input, your execution will get slowed down. So these are few examples. And all this abstraction will help us to deal with complexity. Okay, so it will hide lower level detail. So if you are recalling the previous slide, whatever the digital design you have, you no need to consider all these details. If you are a programmer, you no need to consider or no need to bother about digital designs. Okay, if you know that, it will be better. But each and every time, it will differ according to the processor architecture. Okay, so this ISA will have interface between your hardware and software architecture. So recall this ISA. So this is ISA. So this blue bar, horizontal bar, this is ISA. So this will help you to interact variety of operating system with variety of hardware. So even for the same operating system, okay, you can execute on multiple devices. That is possible. You can execute on HP processor, HP laptop. You can execute in Dell using Windows 11. So this will act like a bridge. Sorry about the same slide repeated twice. Okay. Suppose if you want to know what kind of machine I want to purchase. So based upon these three questions, okay, you can find answer. What is the best performance you need to achieve, and what is the least cost you need to invest, and what is the best cost to performance ratio. Take example of mine. My case, I want to execute parallel program. I want to execute GPU based computation for a large language model. So if I'm looking for a laptop in the market, minimum I need to invest 1.2 lakh, okay, with graphical processor to execute quantum simulation. Okay, so what I did, I searched multiple websites, multiple vendors. I looked for refurbished laptop. Okay, came under Lenovo. That refurbished laptop have minor problems with hardware manufacturing time. Okay, the company will refine that process. They will fix. They will resell through their genuine website, through their official website. Okay, so 1.25 lakh laptop I bought through their website under 33,000. Okay, so you need to answer this question before investing in hardware. So what is your purpose, and what is the best price you can get from the market, right? So this is one more design perspective. So you should not basically go for best performance. Okay, according to the application, it will vary. For my requirement, this laptop configuration is enough. But if I want to scale up to 10 QB, up to 12 QB, I need to invest 2 lakh laptop. I need to invest in 3 lakh laptop configuration. Okay. So based upon your design perspective, again, you need to ask all these questions. And both are required basically if you want to do for comparison and to do metric for evaluation. So you can do a check. Okay, today after the session, go and check your laptop or CPU, what kind of hardware you have and what kind of performance you are getting, what is your investment and what is your return out of your device. So please go and check all these details. Because before buying this laptop, so I used a laptop having configuration about 4 GB RAM. Okay, from 2020 until 2025, I used that laptop for all my quantum computation research. Okay, it will blow most of the people's mind. It is not due to your computer architecture. Most of the simulations and experiment you can do using online server. So don't unnecessarily invest your investment in hardware. Okay, that's my suggestion. So if you want to fully utilize your CPU performance, so most prominently you need to ask what is the response time. So if you are giving a job, if you're executing a job, you need to measure from starting time to end time. Then you need to calculate your performance, your laptop or CPU. Okay, most probably we need to maximize performance through code profiling. So this is the generic formula. Okay, so always performance inversely proportional to execution time. The less it will take, the more it will do performance. All right. So this is what the general reference you can do. Whatever you are executing in your laptop, okay, the same thing if you are executing in CPU, will get more performance for the same investment. So what I suggest, don't invest in laptop until you need to have mobility. Always invest in CPU. Always in CPU, because you can do more upgrade and you can get more return on investment for your hardware. Okay. So this is the important definition in computer architecture is throughput. It is the total amount of work done in a given amount of time. Okay, so this throughput could be a deciding factor about your algorithm performance or device performance. If you are doing research, you can calculate throughput in classical aspects. Also, you can compute throughput in quantum also. Okay, so there is a equivalent word for throughput in quantum, which is called quantum volume. Quantum volume. Go and refer IBM website. They created this parameter about if you want to evaluate quantum performance or quantum computer performance, you need to measure in terms of quantum volume. So what is the idea of CPU performance? You always try to decrease response time to increase to improve your throughput. So always you need to increase your throughput by reducing the response time. So if you want to calculate, your performance factor, then you need to calculate the elapsed time for your given task and the time spent on over your task. Okay, so these are the formula. You can calculate after the session. You try to run any program in your CPU. Okay, try to calculate execution time according to your laptop. Okay, the same program you try to calculate in different machine specification, maybe higher end, maybe lower end. The same program you try to execute in Google Colab using server, then try to compare. So according to the computer architecture, the CPU execution time will vary. Right? So until this, any doubts, you can put in chat box. You can put in chat box. Shall we proceed? Great. Okay, fine. Okay, fine. Yes, I will go back to previous slide. Okay. So this is response time. This is response time means when you're giving any task for your computer, executing your program in simple terms. Okay. You need to measure when you give task for your system, you need to note down the time. Okay. Then your computer will give output for you after completion of your task or program. Then you need to measure the time. So that is called response time. Okay, the more it will take execution time, the less the performance. The less it will take the execution time, you can consider the more performance you'll get from your system. The same program, if you're executing in your laptop, will take less time when compared to CPU. Okay, great question. Great question. I'll go outside. And I will give you CPU versus GPU. I try to show like an image. This is CPU. So generally, if you have processor in your laptop, in your CPU, okay, you contains processor. So this is general. I am not able to see this image. Okay, no issue. We go for Intel, most probably. No image. If they are giving the image, then will be easy for us to visualize. Okay. So this is CPU. CPU contains RAM, random access memory. It contains cache memory. It contains control unit. It contains arithmetic logic unit. So it will do arithmetic operation, logical operation. Okay. So this is the architecture of CPU. GPU means graphical processing unit. Okay. Most probably, if you want to process your images, if you want to process audio, if you want to process video, then you need to go for GPU. Okay, GPU contains the same architecture like CPU, like memory, but this is shared memory. Okay, so you can look, it will contains huge number of blocks, arithmetic logic unit and control unit, and these two belongs to multiple memory units, processing units. Okay, so it contains more number of cores, more number of threads. So that is why if you have GPU, if you are playing game, if you are doing video process, it will be much more easy. So this is general purpose device where GPU specifically designed for graphical purpose device, graphical processing device, you can consider in such a way. So all your images, all your video, all your audio will be stored in the form of matrix. More and more matrix operation can be done using GPU. We'll discuss DRAM. Wait for some slides. Yeah, it is not integrated. It is not necessary to integrate because for few users, no need to go for graphics. Okay, no need to do graphical processing. Okay, so if you want to do graphical processing, then only you need to GPU. So GPU will add additional cost for your system. Suppose if you want CPU for browsing, no need for GPU. Okay, if you want to do a video rendering process, then you need to GPU to do that process. So CPU will do all kind of process. Okay, but GPU only dedicatedly designed for graphical processing purpose. Is it clear, sir? So adding GPU having additional cost. It is not needed for each and every one. Is it clear? Am I answered your question? Great. So to understand this, we need to understand how CPU works. So CPU works based upon clock pulse. So most of the clock pulse generated from crystal, okay, quartz crystal. So your processor contains quartz crystal. So if you are giving power supply, it will vibrate. Okay, it will generate frequency, it will generate signal. So these signal will used for computation. Yes, I will check queries. Wait a second. CPU execution time 1 multiply division y. Okay. Yes, we can run video within CPU without GPU. So you can view video, you can listen audio, you can watch video also without GPU. But if you want to process audio, if you want to process video, okay, then you need GPU. If you are using without GPU, it will take large amount of time. Your computer will crash down if your video length is huge, if your image size is huge, if your audio size is huge. So without GPU also you can do, but it will take longer time. Is it clear? So without GPU also you can run. To perform quantum computing in our laptop, what specifications should we need for performing optimization techniques? So to use quantum computing, to do quantum computing, your normal laptop is enough. If your laptop contains 4 GB, that is more than enough. What I did for past 5 years, I used 4 GB laptop. I used Intel Gold processor. I bought in 2020 only for 25,000 rupees. Okay, most of the time you need to shift all your computation to server. So don't use your laptop as much as possible. Unnecessary. You can use Google Colab. You can use Google Colab. If you want to do quantum simulation within your laptop, then you need to consider a system configuration. In upcoming sessions, we will discuss. So we'll discuss. Thank you. Great audience, interacting, asking questions in between. Okay, so it will generate signal. It will generate with a huge frequency. So more number of frequency, more computation you can do. Okay, so this is one clock pulse, clock period. So it is the entire period. So within this entire period, what you can do, you can do data transfer or you can do data computation. So two operations generally you can do in computer. You can do data transfer between one device to another device, or you can do computation within your device or among the device. Okay, so this is the updation state. You can see downside. So within the each cycle, dedicated for transfer, dedicated for computation. Same way you can have input clock cycle and output clock cycle. During input clock cycle, all input devices will communicate with your system. During output clock cycle, it will give all your output data. Okay, same way you have read cycle, you have write cycle. So multiple terminologies are there. Multiple terminologies are there. So if you want to do one operation, then you need to have constant rate of clock cycle. So we are having a time clock, right? We are having watches. So all these watches have a periodic pulses, a periodic movement. Then only we are able to do all this stuff, okay, in a constant rate. Okay, so how will you calculate a clock period? And you need to calculate frequency or duration of your clock cycle. So PS is picosecond and NS is nanosecond. Okay, so this is an example. So if you identify your clock period, you can identify performance of your CPU. So today this is one more task. Go and check your laptop, go and check your CPU. What is your processor frequency? What is your clock pulse? One more question is there. I try to answer. Rising edge clock, falling edge clock, processing CPU, when it will be used. Okay, to answer this question, I need to answer in different way. Okay, so consider analog signal. Consider analog signal. This is your analog signal, right? This is your analog signal. So if you want to convert this analog signal into digital, what we need to do, we need to discrete this signal level. This is here is we need to discrete this signal level. So this is level 1, this is level 2, this is level 3. So imagine we have 3 levels. So we need to name these 3 levels with binary data. So this is 0, this is 0, 1, this is 1, 0, this is 1 1. Okay, so if we convert, this will convert in this form. So this is your analog signal, this is your digital signal. Okay, so this is continuous in nature. This analog signal is continuous in nature. This digital signal is discrete in nature. So this is rising edge. Okay, this is rising edge. This is falling edge. This is falling edge. So this is the analogy between analog signal and digital signal. To convert analog into digital, we need multiple layer. The more the layer you have, the more originally you can create the analog signal platform. Okay, so one more thing you need to remember, if you convert analog signal into digital, you will lose information. Okay, these are the information we lost, right? These are the information we lost. We cannot exactly reproduce the original signal. Okay, according to our digital signal, we need to reproduce analog. During that time, we will lose some information. Take an example of classical film for camera. If you're taking a film camera, you can zoom, you can enlarge up to n number of times. Okay, but if you're taking photo using a digital camera, if you're zooming, your information will get blurred out. Okay, this is the problem with analog and digital. In some cases, analog will never broke down. You can zoom n number of times, but in digital, if you're zooming, you will get that pixel value because you discretized and you convert it into digital signal. More if you zoom, you can easily find out. More you can zoom, you can easily find out. So we go away from the topic. So I need to calculate clock cycles per instruction. Okay, so all instruction will not take the same amount of time. Take an example of read instruction. Take an example of write instruction. Imagine if you are reading a book, what happens? It will take lot amount of time. Okay, imagine if you are writing a book, it will take much more time when compared to reading. So this is the basic difference. So each and every operation in your computer will take different amount of time. So this is one more formula. Suppose if you want to calculate clock cycles for the given problem, okay, then you need to calculate how many instructions are there for that program and what is the average clock cycle per instruction in your CPU. So if you calculate this, you can calculate the entire clock cycle for a given problem. So this is called CPI. So this is one key parameter if you want to understand your computer architecture and performance. You need to calculate the average number of clock cycles for each number of instruction to execute entirely. For instruction A, it will take 1. For instruction B, it will take 2. For instruction C, it will take 3. So according to this, you need to classify. Take an example of writing exam. Suppose if you are conducting midterm exam, you will get 1.5 hours. Suppose if you want to conduct end semester exam, you will give 3 hours. So according to the intensity of exam, the time will vary. Same way, according to the instruction classification, the execution time will vary. So to calculate the effective CPI, we need to calculate the different types of instruction. Okay, you have n number of instruction. So you need to calculate from first instruction until n number of instruction, and according to the instruction cycle, you need to calculate the overall effective CPI. So IC represents number of instruction belongs to that particular class. So in between, if you have any doubt, you can ask me. In between, if you have any doubt, you can ask me. So nobody asked for a break. That is great to know. Shall we go for break? I need 5 minutes to drink water. Okay, thank you. So give 5 minutes. We will join 5:10. Okay, we'll start. So I'll skip all these slides. Contains lot of information. Okay, so this is the summary of previous all these slides. Suppose if you want to measure your algorithm performance, then you need to calculate the CPU time. You can break down your program into number of instruction and how much instruction will take time for each and every clock cycles, and each and every clock cycle how much it will take per second. Okay, so if you calculate, you can directly calculate CPU time for your given algorithm. Okay, so your CPU time definitely going to affect performance of your algorithm. Okay, so whatever you do research, okay, side by side you are able to comprise all these detail, you can generate as a report, you can easily get publication out of your algorithm. Okay, simply if you do these calculations. So this is one trick I can give for you. So this is the power trend for each and every generation of processor. You can see the clock rate keep on increase, but after some point of time you are not able to increase your clock rate. So faster your clock rate, the faster you can do all your computation, but you cannot increase clock rate just like that. Okay, so clock rate have saturation point. You can see each and every clock rate also increases your power consumption. So next time if you buy laptop, check your processor specification, what is the frequency range it will operate, and what is the power consumption of your processor. So nowadays processor, it will contain 3 or 4 core. So one is CPU general. So CPU contains multiple core. It contains 2 means it is dual processor. Okay, it contains 4 processor means it is quad. If it contains 8 processor means it is octa. Okay, so likewise you check your laptop or CPU after the session. Okay, then it will contain GPU. Okay, nowadays it contains NPU, neural processing unit. Okay, so GPU will do all matrix kind of operation. GPU will do all matrix kind of operation, where NPU will do neuron kind of processing unit. Okay, which is very, very new processor in today's AI laptop contain all these model together. So if you are looking AI laptop category, which cost you more, because it contains multiple types of processors. Okay. Anybody heard about TPU? Anybody heard about TPU? Put in message. So can you describe, sir? What is TPU? Tensor processing unit. Great, great. So what Google did, so GPU has some limitation. So they created TPU. So I tried to show in the image form. Okay. Yes. Great, sir. Great. Yes. So this is the idea. I try to show only the image. So CPU is general purpose computation. GPU dedicatedly designed for graphical processors point, more related to matrix operation. TPU will do tensor product. So if you do all tensor product, okay, tensor operations, then you can go for TPU. So TPU is more powerful computational model when you compare all these three. Okay. So tensor operation is much more complex when compared to vector operation or matrix operation. Okay. So tensor is much more multidimensional, much more multidimensional. So if you go Google provides TPU servers. So this is Google TPU. This is Google TPU. They have dedicated TPU server. Much more faster, you can do most of the computation with a fractional amount of time. Okay. Now we are running out of time. What I can do, I can cover important slides. So this is the component of computer we covered in first session. Okay. So it contains different types of memory, main memory, secondary memory, cache memory. So if you go for cache, which is very fast and small, if you go right side, which is slow and large. Okay. So this is the CPU dice. Okay. This is the fabrication model. Okay. Based upon this model, they will produce processor. They will produce processor, manufacture processor. So it is like a photo film. If you remember analog camera, we used film. The same type of analogy we have. Okay. Using these dice, they will produce manufacture processor unit. So this contains core. Okay. It contains multiple core. This is quad core. Okay. It contains shared cache memory, which is L3 case. It contains memory control. So it contains billions of devices. It contains billions of devices. So this is the core area. This is the core area. If you break down core area, it contains multiple units, contains execution units, it contains data cache. Okay. Maybe I'll cover this, then I will go for quantum. So normally your processor is attached to memory units, multiple types of memory, L1 cache, L2 cache, then main memory, then it will go for secondary memory. If you go for downside, it will increase distance from the processor in access time. Okay. So if you're writing program, you need to keep in your mind, your program will contain few number of lines, few number of operations. So it will store in less amount of memory. So if your program is very small, you can store entire thing in cache memory. If your program size is large, abruptly you need to store in main memory. Okay, if your program is so much large, if your computation is so much large, then you need to access your secondary memory. Then your algorithm performance will affect. So this is the size they mentioned. So this is entire course. If I try to cover within 2 hours, it is almost impossible. Sorry about that. Even though I prepared 130 slides, I cannot cover. Okay. Now we discuss about quantum computing architecture, quantum computer architecture. So if you understand computer architecture, it is similar kind of architecture by using quantum mechanics and quantum physics. So we're going to discuss superconducting quantum computer architecture. So this is one type of architecture we're going to discuss. Like this, multiple quantum computer architectures are there. So the fundamental block of superconducting quantum computer is built upon quantum particles. So these quantum particle could act like qubits. So qubit will act like quantum bits. Qubit will act like quantum bits. Okay. So bit stands for binary digit. Bit stands for binary digit. Okay, so these qubits could be an electron, could be a photon. It could be any subatomic particle. It could be any subatomic particle. Okay, so these qubits contains, these subatomic particle contains properties. So these are properties. Take an example of electron. Electron could contain spin property. Photon could contain spin property. So we are using this property to represent our data. So what is the data we going to represent? We represent binary data. Binary data. Take an example of electron spin. If it will spin upward or it will spin downward. If it is spinning upward, we can represent 0. If it is spinning downward, we can represent 1. Okay. Same way go for polarization. So vertical polarization, horizontal polarization. So 0 for vertical, 1 for horizontal. Okay. So each and every qubit will exist in superposition. So most of you already know superposition. So some of you, if you don't know superposition, we will cover in subsequent classes. Okay. So for single qubit, you can observe superposition. For multiple qubit, you can observe entanglement. So this is the general law. For observe superposition, you need a single qubit. For observe entanglement, at least you need 2 qubits. Suppose if you want to write quantum algorithm, then you need to understand this quantum computer architecture. Okay. So these quantum computer algorithm are built upon quantum logic gates. So these logic gates will operate on quantum particle. Suppose if we chose electron, okay, your quantum logic gates will operate on electron. Suppose if we chose photon, these quantum logic gates will operate on your photons. So in this case, we chose electron. So in this case, okay, so what is the advantage of using quantum computer? So you will get computational speed up. So how much speed up you will get? You will get 5%, you will get 10%, you will get 100 times, you will get 1,000 times, million times, billion times. That is possible in quantum. But in classical, this limitation is very huge. You cannot have exponential speed up. But in terms of quantum, you get exponential speed up because you're doing computation simultaneously. You're doing computation simultaneously. So finally, if you do measurement, you will get result in very high accuracy. So this is two huge difference between classical. One is computational speed up, one is high probability, high accuracy. So only for these two reasons, more we are going for quantum computation when compared to classical computation. So for that, we need to have a specialized hardware. Okay, so what kind of hardware we need to have? We need to use ultra cold temperature. We need to reduce ultra cold temperature. So here we need to reduce temperature. So layer by layer, we need to reduce temperature. Okay, so this is called quantum processor, quantum core. Quantum core contains quantum processor. Okay, so here you will reach temperature near to absolute zero. Near to absolute zero. You cannot attain minus 273 degree, but near to the temperature we able to attain. Okay, by doing this, what you can achieve slowdown of your quantum particle, because your quantum particle is always in random motion. Okay, if it is always in random motion, you cannot use that particle for computation. So to slow down that quantum particle, you need to reduce temperature, you need to maintain. So how we are doing? You are using microwave pulses. So all these wire will carry microwave pulses. Okay. By using your microwave pulses, you are able to control your quantum particle. Okay, you are able to do computation. After processing, it will give result in the form of microwave pulses. You need to read out. So you can read out with the help of measurement. So this is a read out operation. And this operation is irreversible. This operation is irreversible. Okay. So now alternatively, you can use laser beam. Okay, you can use trapped ion. Okay, to construct a quantum computer. So don't come to a conclusion. This is only architecture. This is one type of architecture existing in quantum computer. So by this, I will wind up my presentation. Thanks for patiently listening. So I hope you could be able to understand something out of this presentation, both from classical perspective and from quantum perspective. Better you understand classical architecture, computation, architecture, and organization, better you're able to understand quantum architecture. So that is the point of this topic. So if you have any doubt, you can ask me. I will share my social media ID. Suppose if you want to connect with me, always encouraged. We will discuss, ma'am. We will discuss in subsequent sessions. We can do quantum computation in real quantum computer, or you can do quantum simulation with the help of your laptop or CPU. So two things you can do: real quantum computation, quantum simulation. You can give connection request, or you can follow me to get update whatever happening within India. I frequently post. Thank you all. Thank you all. Yes, we'll cover in subsequent sections because time is almost completed. IBM Qiskit is open source. IBM Qiskit is open source. We'll discuss that. In terms of power consumption, quantum computation will take very less amount of power when compared to conventional computation. So if you go for green computation, green energy, quantum computation is one of the best we can do. We will cover this Qiskit part, man. We will cover. So don't worry. This is the first class. Definitely will cover. I will cover superposition, entanglement if time permits. Definitely. Thank you. Thank you. Thank you. To go for main window, the bugs. Recording is available. I hope you will get. Anybody from ASIC Academy? Completed
Yes.
session, sir.
Thank you, sir. Thank you so much for the session.
Thank you, sir. Thank you. Thank you.
Thank you.